over into chapter 7. We're going to start chapter 7 today. And so your quiz is going to have a few questions from chapter 7 as well. Okay. So I'll give you a couple of seconds just to recalibrate and probably open up these new notes. So this is membrane potential. And our first objective here is to explain the ionic basis of the resting membrane potential. Super important topic. We're going to continue to build on this as we talk about the action potential. And so we're first going to talk about how the conditions that are existing inside a cell at rest, how did those conditions come about? How do we establish the resting membrane potential? So the resting membrane potential really is what's happening in the cell at rest. We know that the value for that in terms of neurons is going to be negative 70 millivolts. But how do we get there? That's what we're going to be looking at today. How do we get to that negative 70? And we know negative 70 simply means that there are more negatively charged particles or anions inside the cell than there are cations. And so how did we get to that environment? So what we're going to do is we're going to talk about the equilibrium potential for potassium. Then we're going to talk about the equilibrium potential for sodium. Why? Why are we going to look at potassium and sodium? Because these are the two most influential ions on the resting membrane potential. The way that potassium and sodium move are the most influential on what that value ends up being, that negative 70 at the end of the day. But we have other ions moving in the cell, right? We've got calcium, we've got chloride, we've got some anions, but the two most influential are going to be sodium and potassium. So we're going to kind of ignore the other ions in the cell and really focus on the movement of potassium, the movement of sodium, and how they play a huge role in establishing the resting membrane potential. Now it exists because there's more negative charge inside the cell and more positive charge outside the cell. All cells have some value as a resting membrane potential. It's usually negative, but it can be anywhere from negative 5 millivolts to negative 100 millivolts, depending on the type of cell and the location. But the cells that we're going to be speaking about that we're really focused on are neurons or our excitable cells, and they have a resting membrane potential of negative 70 millivolts. And so we're going to spend some time talking about where that negative 70 actually came from. So in order to talk about the equilibrium potentials, or in order to talk about the resting membrane potential, we really want to start the conversation by looking at the equilibrium potential for sodium and potassium. And we also want to talk about the two important factors that determine this potential. First of all is the fact that we have an ion concentration gradient. So the simple fact that we have these relative ion concentrations, we have a different number of ions outside the cell than we have inside the cell. And so this creates these concentration gradients across which our ions want to move according to their chemical driving force. So remember, these ions are going to be impacted by concentration gradients, which is the chemical driving force that wants to act on these charged particles. So that's the first factor that's important in determining this resting membrane potential. The second factor is going to be the permeability of the membrane to these ions. Now, when we say permeability, I really want you to be thinking the number of ion channels that are in the membrane. Because remember, an ion is a charged particle, so it cannot traverse the phospholipid bilayer on its own. It must go through one of the one of the channels that we described last unit, which is an ion channel. And so when we speak about permeability, we're really just talking about how many channels are in the membrane for this ion. How leaky is the membrane to this ion, which is really a reflection of the number of ion channels. Now this table helps to describe and define some of the terms as far as potential. So we've got different types of potentials in our physiologic systems. We've got membrane potentials, which we're going to be speaking a lot about today. We're really talking about the resting membrane potential. There's also graded potentials, which we'll talk about in terms of the synapse in a couple units down. And then there's the action potential. So I don't want you to memorize this table per se, but I really want you to be extremely familiar for the sake of being able to discern different types of potentials that may be, on an exam or on a quiz, so that you can understand what's being referred to, as well as just as we're speaking in conversation, you being able to understand what potential I'm referring to as I'm using some of these different terms. We kind of introduced the equilibrium potential already. So again, not memorizing here, but just being really comfortable in understanding the difference between some of these potentials. So this brings us to speaking about the sodium-potassium pump. And we introduced the sodium-potassium pump already. We talked about it as it pertained to the primary active transport. We said that it was on the epithelial cells as well. Does anyone remember what surface or what side of the epithelial cells the sodium-potassium pump lives? Can anyone recall where the sodium-potassium pump is on the cell? Is it on the apical surface? Is it on the basolateral surface? Excellent, thank you. So it's on the basolateral membrane. So our epithelial cells have this sodium-potassium pump. Our neurons as well have the sodium-potassium pump on the basolateral surface. And so the sodium-potassium pump generates or helps to establish the resting membrane potential. 20% of that resting membrane potential is directly owed to the sodium-potassium pump. What that means is that we've got this pump that's pumping 3 sodiums out of the cell and 2 potassiums into the cell. And so when we think about the net movement that's happening there, if I've got 2 positively charged ions, they both have the same valency, so they're both monovalent or having 1 charge. And so if I'm pumping 3 of them out and 2 of them in, a net 1 plus or a net 1 positive charge is leaving the cell. And so that in and of itself creates a more negative environment inside the cell. So 20% of the resting membrane potential is directly a result of the sodium-potassium pump. 80% of the resting membrane potential is indirectly related to the sodium-potassium pump. So because the sodium-potassium pump, again, is pumping sodium out, pumping potassium in, we now have these gradients that are being established where sodium is higher outside the cell because of all the sodium that's being pumped out. Potassium is lower inside the cell because of, sodium is lower inside the cell. And so now we have a sodium gradient where sodium can leak from the outside of the cell to the inside of the cell. So passively or indirectly because of that sodium-potassium pump. Same thing is true for potassium. Because we're pumping potassium into the cell, we now have a lower potassium concentration outside the cell, a higher potassium concentration inside the cell. And so now potassium has a gradient where it can leak from the inside of the cell to the outside of the cell according to its concentration gradient. So 20% of the membrane potential is directly owed to the pump, just pumping more positive charge out. 80% of this resting membrane potential is an indirect result because of the gradients that are being created by the pumping of these ions, sodium out and potassium in. Now, as we talk about a typical neuron, we really want to look at the permeability of a typical neuron. This is really going to be important as far as the movement of our ions. And so a typical neuron is 25 times more permeable to potassium than it is to sodium. And if you think back to what I just said about the word permeability here, this simply means that there are 25 times more potassium channels in a neuron than there are sodium channels. So potassium can move much more freely through the membrane than sodium can because it has more access, more channels to do so. We also want to look at the relative ion distribution across the typical neuron. Outside the cell, there's sodium and chloride. Inside the cell, there's potassium and other organic anions, which have a negative charge. And so initially, we start out with this balanced scenario where the positive charge of sodium is being balanced by the negative charge of chloride, And on the inside of the cell, the positive charge of potassium is also being balanced by the negative charge of the organic anions that are inside the cell. So we kind of start off with this balanced scenario where we have equal positive and negative charge on the inside and the outside of the cells. So as we really begin the conversation in terms of what happens, what are the events that happen to establish that resting membrane potential, we're going to look at two hypothetical scenarios. The first hypothetical scenario is that we've got a cell that is only permeable to potassium. So we'll talk about a cell, a hypothetical cell where there's only the movement of potassium at first. Then we'll talk about a hypothetical cell that only allows sodium to move. And then we'll kind of bring those two parts of the equation together and look at how both the movement of both ions contributes to that negative 70 millivolts. So our first scenario here, we've got a cell. We're looking at a cell where only potassium is moving. And the first thing we're looking at is the concentration gradient of potassium. So we know potassium has a higher concentration inside the cell than it does on the outside. And again, just to recap from our memory here, this is because of that sodium potassium pump that's pumping to potassium in the cell. And so we've got more potassium in than on the outside. So now there's a concentration gradient that's set up, or a chemical force that's set up, where potassium wants to move from the high concentration inside to the low concentration outside. So that's the first thing we establish. Potassium's chemical driving force that's created because of the concentration gradient of potassium. The second thing is we want to now look at the electrical force, because we know that all of these particles, they're being acted upon by two forces. So while we're considering them separately, we really don't want to neglect the electrical force as well. So the second thing that happens here is we think about what happens as potassium starts to move according to its concentration gradient. It starts to move from the inside of the cell to the outside of the cell. And so now we've got this positive charge leaving the cell. It's leaving behind the unopposed negative charge. So remember, we had inside the cell, we had potassium and the organic anions, just to remember where that negative charge that's remaining is coming from. So potassium and the organic anions. So if all the potassium is leaving according to that chemical driving force, what's left behind is the unopposed negative charge of those anions that are remaining inside the cell. And so now we create this negative environment inside the cell. And so the second part of the equation here is that we've got an electrical driving force that wants to drag potassium back inside the cell. So essentially we have a chemical force wanting to move potassium out of the cell. We've got an electrical force wanting to move potassium because it's positively charged, because the inside of the cell has now become negative. It wants to move potassium back to that negative environment inside the cell. So we've got two opposing forces for potassium. So now the cell eventually gets to equilibrium, right? When we got the movement of these particles in and out, and then we get potassium arriving at its equilibrium potential, which happens to be negative 94 millivolts. And when that occurs, we've got no movement because, if you remember what the equilibrium potential is, we've got opposing forces that are equal in magnitude. And so we have zero movement because those two forces now cancel each other out. Okay, so that is potassium and potassium movement. And this is how we get to that negative 94, which is potassium's equilibrium potential. And just to kind of go a step further here and describe what this is really referring to, what this negative 94 means. Negative 94 means that at this membrane potential, potassium is no longer moving. It's at equilibrium, okay? And so just to recap here, an ion is at equilibrium when there's no net force for it to move across the membrane, i.e. the chemical force is equal to the negative electrical force, or there is zero electrochemical force, right? So the electrical and chemical force cancel each other out and we see zero movement.